So hi everyone, I'm Aditya Akella. I'm also a professor at UT Austin. I've been here for 4 years. Before that, for about 20 years, I was a professor at Wisconsin. And I just want to quickly mention a couple of things we do at UT. So I am the lead PI of the Learning Directed Operating Systems Expedition. This is an NSF program. It runs over a 5-year period. And essentially, we are trying to build the next generation of Linux, if you will, that is powered by AI-driven decision-making and AI-driven data paths. LDOS, as we refer to this learning-driven operating system, is basically re-envisioning the operating system from machine learning lens. More broadly speaking, there are many other computing systems and technologies that are ripe for AI-driven reimagining. So an example is mesh networking. There are others like cloud computing, vehicular networking, autonomous driving, that are all computing systems, distributed computing systems, but written like old-style systems. So as part of a broader effort called Infra AI, we are actually looking to see how can we rethink broader computer systems, distributed systems, and networking through the lens of AI. And a lot of this work is being done in collaboration with industry, hyperscalers, but also startup companies, and we'd love to collaborate with Spec 5 and other people here to understand how we can bring what we are doing to the things that you are interested in. All right, so let me start with Networking 101, just so that we level set here, right? So the traditional view of networking is that you have applications that want to communicate. Applications run on machines or hosts, and there is a networking stack that sits underneath them, moving data, right? And then once the application wants to communicate to the other end, it sends the data. The network stack does things to the data, packages it, sends it to the other end to make it amenable for consumption by the receiving application. Now, there are two aspects to networking that I think fundamentally come in the way of what applications, interesting applications we can realize on networks as they stand today. The first is that the contract between applications and network today is very rigid and narrow. And what I mean by this is that typically you connect and you send bits over the network, and the assumption is that the network is going to deliver the bits, right? Now, that's fine, but not all applications need all the bits to be perfectly transmitted every time. So this is a very baked contract between applications and networking, which many applications may not care about, right? Video conferencing, for instance, I don't care that I see every pixel in Dayok's persona. I just need to know it's Dayok talking to me. That's one part of the contract that's very rigid. The other thing is that once the application takes its bits and shovels them into the network runs a bunch of algorithms to decide, oh, I need to reliably deliver those bits. I need to make sure I'm not overwhelming the capacity of the network. And so there is a bunch of heuristics that are implemented inside the networking stack that essentially realize reliability, things like flow control, congestion control, and so on. But all of these heuristics are manually designed. Like if you look at the Linux code, this is thousands of lines, tens of thousands of lines of manually written code that decides how to assure reliability, how to get congestion control, flow control, and so on. So these are also rigid because manual code evolves at a glacial pace. What I'm going to argue is that these kinds of attributes are actually what result in applications experiencing poor performance. The rigidity in the contract and the rigidity in the algorithms that the network stack implements force applications to behave in ways that prevent them from adapting to dynamic environments. For example, in the context of mesh networking, where bandwidth is varying or latencies are highly variable, such as some of the examples that we saw in the presentation that Dayok made, applications cannot expect the network stack to adapt to the capabilities or the constraints that the network is inducing. My argument also is that the rigid, narrow contract of the network fundamentally also constrains the kind of applications we can run today. Ultimately, the amount of information applications can exchange, is traditionally bound by, information theory, right? Shannon. However, if you think about it again, it really depends on what information you really want to exchange. If I really want to send all of the bits to you, there is a certain bound of how much capacity you need to do that. But if I think about the semantics of the communication, the bound completely changes. And by thinking about the bound with a new lens, you may be able to open the door to interesting classes of applications that are not possible today. So this is kind of where I think AI comes into play. With AI, I believe that you can change the contract between applications and the network. You can also change the way the network takes bits and moves it across network pipes by building better controls. And what I'm going to argue is that this gives rise to applications that can better adapt to dynamicity, achieve better performance, and also potentially enable applications that are simply not possible to run over constrained networks or systems today. All right. So what is the basic idea here? The basic idea is to think of AI as a semantic compression engine. And I'm going to talk about what I mean by semantic compression. But the upshot of viewing this as semantic compression is that the contract between applications and the network is one of extracting the intent of the communication, not the exact bits that you want to exchange, which unlocks a richer set of applications. And the other view of semantic compression as you apply to network state is that compression, or thinking about the use of AI, allows you to extract the semantics of the network state that allows controls to operate in a more intelligent manner on top of the network state. Okay? So I'm going to give you some examples of how you can use AI and its capabilities to better contextualize the environment in which applications are trying to communicate, to do the minimal work necessary to get effective communication going, where effective is tied to what the application or the end user expects. Okay, so overall, I don't want to change the interface of applications today. You still write applications using your traditional libraries. All the things that change are underneath the covers, behind those APIs. All right, so let me get into what I mean by semantic compression. And there are three possible ways in which, or places where you can do this kind of compression. One is in terms of state. And this can happen locally, like on my phone or at my machine. The system state that there is, always it evolves as you run applications or you shut down applications. I can apply semantic compression there. I'm going to talk about why that's useful. A more broader scenario where semantic compression comes into play is state across machines in a distributed setup. Not just a local state, but if I am communicating with Dayok, then the state we share with each other with respect to the communication we currently have. And the final place where semantic compression comes into play is in the intent, in applications communicating with each other, representing the intent of the communication in a semantically compressed manner. Okay. Any questions before I dive into what this compression means and how we can leverage it so far? Okay. So let me start with the simplest thing. This is the local state, right? So here's what I'm calling a controller. A controller is something like, if you're watching a video, there is a bitrate adaptation engine that is running inside your browser and at the remote server that's deciding at what bitrate to encode videos to send to you. If you're in a lower bandwidth situation, it's going to downscale the encoding, otherwise upscale it, right? So that's an example of a controller. The way these controllers work is that they look at state. They look at, okay, what did I observe in serving you in the past, and then use that information to decide what to do next. An ideal controller needs to have a clear idea of what's going on at my client to decide how to send to him, right? And given that information, you can take an action that is tailored to the precise current state. Unfortunately, if you look at any of the controllers today, they rely on approximate state. They kind of take running averages of various high-level metrics, and I'm going to get into examples of that. And they kind of sample the previous chunk of video I sent to you and what the rate was, kind of take historical samples of the performance. And on the basis of that, they tailor the action. However, the state that I'm using to send data to you today is stale. It is based on my past transmission to you, and it's also inexact because it's derived from these highly summarized metrics. So it's losing a lot of contextual information that makes it important to deliver data to you effectively. All right? Now, why does it matter, right? So if you think about what all matters to the state that I need to be aware of when I'm sending data to you, it's impacted by a lot of things. It's impacted by what other application is co-running alongside my sending video to you. It's impacted by my past choices or my anticipated future choices of the bit rate. It's impacted by other algorithms that are running inside the network, like the network changing paths or a failure happening, and a lot of other things impact the incipient state of the network. And because of all of these, you can imagine that there are a lot of latent factors that are affecting the state in many possible ways. The issue, though, is that if I were to just think about taking the entire set of interesting bits that capture state and funnel that into some very simple running average of previous throughput, then I'm actually losing a lot of interesting information, and I'm losing a lot of interesting context, right? So today's approaches that kind of approximate state, take these running averages, I would claim have very limited representational power. They cannot represent current state in the best manner possible, okay? So this is what I mean by the state problem, right? There is a representation problem. So how does AI help over here? And let me talk about the example of semantic compression here. If you think about a large language model, one way to interpret any large language model like ChatGPT today is that it's a compression engine. If I were to prompt a large language model, it's going to come up with some sort of an embedding for the prompt. And that embedding has a lot of power. It can be predictive. It can generate the next token. It can write a poem, whatever, right? But why is that embedding effective? It's not just encoding what's in the prompt, but it's also encoding knowledge of English in deciding how to interpret the prompt to determine what comes next. So it is actually compressing a lot of information about all of the knowledge of language into the embedding for the prompt. So that's what I mean by representational power of an embedding. Can we bring the same kind of representational power to network state? And the idea here is that if I think about any application that's running on a system, it's generating a lot of state metrics. Like if I look at /proc on Linux, I'm going to get a lot of variables of how many bytes were delivered, packets lost, cache hit rates. There's a lot of state, right? Can I use that state, runtime state, to train an AI model that has the same representational power as LLMs today? And that's basically what we're getting at here. So we built a state embedder called Unum that's going to essentially take tokens. These tokens are snapshots of state that were seen at various instances of time in your system, now 10 milliseconds ago, 10 milliseconds prior to that, and so on. We train a model such that the embedding that you get is it takes a certain sequence of windows of state, and it has predictive power. It can tell you what is the current state and what will the next state be, right? So that's what I mean by a state embedding. We train this transformer in an encoder-decoder model, just like transformers and LLMs are trained today in a next token prediction fashion. And instead of using both the encoder and decoder, we drop the decoder and just look at the embeddings that come at the end of the encoder. Now, what do these embeddings represent? They represent rich semantic information, whatever can be gleaned from snapshots of system state over some period of time. Right? Now you see how we don't rely on average metrics anymore. We look at multiple snapshots, and we not really, one way we could do this is we could take all of these raw tokens and actually feed that into a giant model, right? That also has this information. However, a transformer has the capability of using self-attention operation that extracts latents more intelligently than raw metrics can give you. All right, so here's how effective this ends up being and how you might be able to use it. So here's you see a series of network observations. You pass them through our embedder. The embedder gives some sort of a state embedding, and the embedding is passed to a controller as a representation of current state, as opposed to running average metrics. And then on the basis of that embedding information, it makes a decision. So we trained a bunch of controllers of this kind. We trained a video bitrate adaptation controller. We trained a congestion controller. And these sequences of graphs show the performance we get as a consequence of our approach. So this is our approach, and these are techniques that simply take a lot of other data, and you can see that we, on average, get a lot of better performance than otherwise. So I want to clarify, so the information I'm passing to the AI model is system variables and dynamic system state. This doesn't directly tie to user-specific information. It's just like utilization metrics. The idea is that if I throw a sufficiently powerful AI model and give it enough data, then by looking at that information, it should be able to tell something semantically useful about the applications and their behavior. So A, this is not super sensitive data. B, this controller is running on the host. It's not inside, it shares the same trust domain as the host. So we are not actually breaking that trust assumption. Typically, if you pull that out and run it elsewhere, then there is this question of what is the relationship from a trust perspective, but we don't really have that problem in this particular context.
You've seen that there are many adjustments that you can make. For example, you can do long fast, you can do short, you can set individual frequencies. If you were to just take snapshots of those, forget about the actual content being sent, but just that setting data, and then you started to time things like, on average, how long before a message is received? How many times do I have to resend something? How large of a message fails on average? How many times? That information will allow you to build an optimizer where instead of you touching any of the settings of the protocol, the system is constantly learning on the fly by message delivery and is tweaking the Meshtastic parameters on its own. So in other words, it's like a little agent that's living within the Meshtastic app, measuring how effective your messages are going out, and rather than you changing anything, it's just using AI to learn and constantly tune to guarantee the best performance possible. That's
exactly right. So that's, and I don't want to sort of belabor the empirical points here, but there is a shaded light blue curve which you cannot really see. Maybe you can. That's the actual bandwidth, and it's varying in a time-varying manner. And this is our technique that uses 10 previous round trips of snapshots of information, encodes them, and as opposed to another approach that doesn't use any of this smart embedding. And we can see that we more closely hug the changing bandwidth and never overshoot, undershoot compared to these other baselines. Yes? This is on the host, yes. Yeah, great question. So, yeah. So this, the transformer we have trained is actually a very simple transformer. It has order few tens of millions of parameters, and we run it on the CPU. So we're not running it on the GPU, no custom silicon. Obviously, acceleration through a custom silicon would help, but for the purposes of this application, we haven't found the use for such a thing. The thing also to remember here is that since this is only building context using system state, it can run as often as you want it to run, right? Because it's only giving you additional assist to do better, right? It's, sometimes I can just decide to turn it off and just rely on my original algorithm or whatever it is that's sending the data, or invoke it whenever I'm under dynamicity. I want to know more, then I turn it on. Right? So we are computing the embeddings in a way that they capture all of the application's effects. Even if you are only running one application, this embedding calculation for one application, all of the metrics that you're collecting are impacted by other applications. So implicitly, you're learning how these other applications are going to function now and in the future, and using that to control your own transmission. So it's actually doing this implicit coordination with other applications in that manner. Okay? Right. So this is just a simple example of semantic compression at one host. Right? Now, you can go one step further, and I can just going back to the example that Dayok had of the 5G MEC. Often controllers don't operate in isolation. If I'm sending, you're receiving, or if I'm a RAN node, there is an edge server at the other end, and there are schedulers or controllers at both ends. And typically, if you make decisions at one end, and both ends make independent decisions, they can end up being suboptimal. Now again, I don't know if I have the time to go into the details. This just shows, if different, for workloads that have specific deadlines, if both of the endpoints ran and the edge server used their locally optimal decisions, you end up with situations where certain jobs miss their deadlines. And if they were to switch to different locally optimal decisions, there's a different set of deadlines that are missed. But the question is, how can we get these controllers to coordinate with each other through the same idea of semantic compression? So the idea there is we use the same approach. Whereas previously, we were looking at local state and predicting what comes next from a local state perspective. Now, I'm going to look at, you and I are communicating with each other, and whatever data I'm seeing locally is a consequence of what you are running at your system. So I can use the way we are communicating with each other to learn about what else is happening at you. So this time, the idea would be, I'm going to look at my local metrics, but I'm going to use that to predict your side. And then I'm going to use that prediction to do my local scheduling. Okay? And that's essentially what this is doing. I'm going to co-train the embedders here in a way that I can use my local state measurements to understand what's going on at the other. And again, in this case, implementing that and doing this implicit, more explicit coordination, we no longer miss any of the deadlines for our deadline-driven jobs. Okay? So this goes from compressing local state to compressing state across two machines and being able to do better with respect to communication and pushing the envelope of applications that can be supported because now you no longer have these deadline misses. Okay, everyone with me so far? Okay, so this is about just how do you take compression and apply it to control. So the thing that I kind of made me think when I was talking to you, Amir, is, well, why don't we push this even higher up? If we are able to use embeddings to represent state and relationships of state between two hosts, can they also be used as compressors of information and communication intent? So here's the idea. The idea would be that you would use these embeddings as compressors of the intent behind communication. So typically, how do you think of compression, right? So if I were to send some piece of data, I would use either a lossless or a lossy compression engine, send the raw bits over the network. At the other end, I would have a lossless or lossy uncompressor. I would get the bits back. But there's a strict, almost one-to-one relationship between a bit here and a bit there, right? But I don't really care about that. What the approach I'm advocating suggests is, you want to send me something. I'm going to use my AI model to not send you the bits, but I'm going to first derive an embedding for what it is you want to say, a semantic embedding that represents something tied to the application you and I are running and the meaning of what it is you're trying to send in the context of that application. I'm going to send the embeddings. At the other end, I'm going to pass those embeddings through a decoder and reconstruct what you intended to send me at the other end. This is sort of like what we do with DALL-E and any other sort of image type application, generative AI type models applied to networking, but pushing it away from just the stack in closer to the application layer. All right? So this is what I'm calling sort of semantic compression of information. So here's an example. I heard there are high schoolers here. Any high schoolers? Okay. Do you recognize what the screenshot is from? Brawl Stars, yes. Okay. All right. So. Yeah, I know, so does my son, so that's why it's here. So this is Brawl Stars, and my goal is to see if we can support kids playing Brawl Stars on the mesh network. So what's happening here, right? So there are, I haven't built this yet, so I don't have any results. Like I said, 2 weeks ago, you made me think about this. But the idea here is that if there are gamers, there is an encoder that's going to create an encoding of your game state and your friend's game state. Instead of sending actual snapshots of game state, you're actually sending encodings, which are more succinct than the actual data, but more representative of what it is you're trying to do in the context of the game. The embeddings go over the network, and then there is a generator that reconstructs what you have from the embeddings. The interesting thing here is that the generator, doesn't need to generate your snapshot and your friend's snapshot. It doesn't actually need to generate this. It only needs a machine-readable output that is very Brawl Stars specific. You need to know where your other co-brawler or whatever you call it is, and he needs to know where you are and what your health is and so on. It's very context dependent. So the generator can actually just generate machine understandable state and send those embeddings back, which can then be used to update your state. So this is my idea for how you can push the envelope from using AI in a systematic way to possibly support interesting applications on constrained networks. Right, so that's all I have. So just a bunch of thoughts to make you guys think. I think this is actually a really exciting domain. I'd love to see how we can take some of the ideas we have and work with you guys closely, but also would love to take any questions or thoughts you guys have.